Alright, to solve this equation, I'm going to let omega equal a general complex number, a plus bi. A and b are then real numbers. So this implies that omega star, the complex conjugate, is going to be a minus bi. Just make the imaginary part the negative of what it already is. Okay, now I can sub in. So I've got a plus bi plus 2 plus 7i equals 3 times a minus bi, so that's just 3a minus 3bi minus I. Now it must be that the real numbers are all equal. So the real coefficients are a plus 2 equals 3a. See, that's it. That means a must equal 1. So I get 2a equals 2. And now I'll deal with the imaginary coefficients. They must also equal one another. So b plus 7 must equal minus 3b minus 1. That means 4b equals minus 8 and b is equal to minus 2. And we're done. Omega is going to equal 1 minus 2i. We're asked to then prove algebraically that for non-zero z, z is equal to minus its complex conjugate if and only if z is purely imaginary. So we need to show that the left implies the right, but also that the right implies the left. Let's first of all do the left to the right. So if z equals minus z star, I'm going to let z equal a plus bi like I did before. And that implies that z star, by the way, of the complex conjugate is going to be a minus bi. Then a plus bi will equal minus a plus bi. I've taken the negative of what I found here. These cancel. It must be that a is equal to 0. And therefore z is purely imaginary. Right, now to do the other way around. If z is purely imaginary, then z equals, for example, bi. This implies that minus z star is equal to minus bi, which is bi, which is z. And that's what we need to show. So result follows. Z equals minus z star if and only if z purely imaginary. So that was an algebraic argument. In part C, we're asked to use, for a different idea, different proof, geometrical argument. But first up, we're asked to state for any z the single transformation which transforms A to B. So I've got z as my point-on-my-grand diagram for z. A is the point-on-my-grand diagram for z. Maybe I draw it here. So I've got x and I've got y. This is my real axis. This is my imaginary axis. I've got x plus iy. If I take the complex conjugate, then the real part stays the same, but the imaginary part becomes negative. So it's going to be down here now, minus y. So it's just a reflection No, we shouldn't say the x-axis. Reflection in the real axis. So now for this final part, another if and only if argument to make, but now geometrically. So I'm going to go this way. So if z equals z star, then z must lie on the real axis. Since reflecting in real axis gives the same point. And this implies that z is purely real. Going the opposite way, if z purely real, then it will lie on the real axis. So reflecting in this axis will give the same point. You have to be really careful here. Make sure we're using geometry and not using algebra like before. And therefore z equals z star. So the result follows z equals a complex conjugate if and only if z is purely real. That's how I did this question. The mark scheme is a little bit more technical, so I'm just going to share that to finish. So z equals z star means A and B are coincident. Okay, I do quite like that. I didn't actually refer to A and B, to be fair. I just said that it would stay in this, z must lie on the real axis. Okay, I think I'm all right. So A must represent a purely real number, so z is purely real. And the other one is if z is purely real, A lies on the real axis, so is invariant under reflection the real axis. Okay, I like those words. I didn't kind of use that technicality. It's nice. The complex conjugate's also represented by this point, so z equals z star. So I think it's hard to come up with this sort of stuff, but yeah, that is like the model answer. I think mine's pretty good. I'm happy with it. So I'm sticking with it. But yeah, well done.